This video explains the concepts of evaluating and solving expressions and equations in function notation, and we'll look at it in four different situations. So the first is given a graph, the second is given a table, the third is given an equation, and the last slide just gives several examples using a graph, and we get into a little bit more detail about the differences between evaluating and solving. So we're going to begin with our first example. It says evaluate and interpret f of 9. The first thing you need to do when you're evaluating is to determine whether the number that you're given, in this case the 9, is an input value or an output value. And we can tell in this situation, because it says the temperature is a function of time, we've got that the temperature is a function of the time of day. What that means is that our input values are going to essentially be the time of day, and the output values are going to be the temperature. So when it says to evaluate and interpret f of 9, we know that this 9 right here is an input value. To evaluate this, we just look at our graph. We look and we see where there's 9 o'clock, which is right there. And we follow up to see, okay, well at 9 o'clock, the temperature is 73 degrees. So to evaluate, we're going to say that f of 9 equals 73 degrees. We can say at 9 o'clock, in this case it's 9 p.m., at 9 p.m. the temperature is 73 degrees. I'm going to assume that that's Fahrenheit. Solving in function notation is slightly different because we're given an output value as opposed to an input value. So when it says to solve and interpret f of x equals 76, we're really asked a question. You can kind of think of it as saying, at what time was the temperature 76 degrees? And you need to think that there could have been multiple times at which the temperature was 76 degrees. So we need to think of this question as kind of our overarching question here. We work backwards, and we just say, if we zoom in on our graph, make it a little bit bigger there. If we zoom in on our graph, we say, okay, well, when was the temperature 76 degrees? I'm going to zoom in right here to 76 and kind of move over and say, okay, well, at 6 p.m. the temperature was 76 degrees. I'm going to kind of continue over a little bit. Were there any other times that the temperature was 76? And no, there weren't. So we've got one solution to this equation. The solution to an equation is an equation itself. So we're going to say x equals 6 is the solution to that equation. We can maybe answer that in a sentence when we say, at 6 p.m. the temperature was 76 degrees. The evaluating part is right here, getting the 73 degrees. The solving part was getting the 6. When we talk about interpreting, we're asking to take that answer and put it in a context. Putting the 9 and the 73 in context in this sentence is interpreting. Putting the 76 and the 6 hours in context right here is that sentence, and that's the interpreting part. For our next slide, I'm going to give you a table. We're going to do the same thing. Evaluate and interpret f of 7. So we look here, we see that this 7, because it's on the inside of the function notation, represents an input. To evaluate, we just look at our table. When was the hour 7? We go over and we see that the temperature at 7 o'clock was 75 degrees. So we'll evaluate and say f of 7 equals 75 degrees. And then we'll interpret that by saying at 7 p.m. the temperature was 75 degrees. Solving is, again, going backwards. We're given this 68, and this is our output value. And this again asks a question. At what time was the temperature 68 degrees? So we're going to go look at our table, and we'll say, okay, well, when was the temperature 68 degrees? And the thing that's a little bit different, a little bit more intricate about this problem is, well, if we look, there's a few times when the temperature was 68 degrees. we've got right here, right here, right here, and right here. So it looks like we have 4 times. So that means that there's 4 solutions to this equation, which is fine. We can say x equals 10, x equals 11, x equals 12, and x equals 1. Now you might be thinking, wait, a function can't have multiple numbers, but you have to be very careful about that. In a function, each input goes to exactly 1 output, and that's exactly what's happening here. 10 has 1 output, 68 degrees. 11 has 1 output, 12 has 1 output, and 1 has 1 output. They're all 68. They all happen to be the same output, but that doesn't make a difference. This is still a function. We're going to look at a function in the form of an equation. Our equation here is h of x equals 68 plus 2x. And we're going to evaluate f of 6. So we know, because this is the input, this is the time. And so we're just going to say, okay, well, h of 6, I'm going to plug that into our equation. 68 plus 2x. We're going to say that's 68 plus 2 times 6, which is 68 plus 12, which is 80. So we just evaluated. Similar situation with solving, only we're gonna interpret this 72 as an output value. So we're not going to plug in 72 because that would mean 72 hours from whenever we started. And so the 72 we know is an output. We know that that's degrees. So we're going to write an equation. We're going to say 72 equals 68 plus 2x. We're going to solve, and we're going to say, okay, well, we've got on this side we're left with 2x after I take away 68. And on this side we're left with 4. So we got x equals 2. And so that means at 2 p.m. the temperature was what we were given as 72 degrees. At 2 p.m., temperature was 72 degrees. Our last slide is given in a little bit more analytical way, and we're not dealing with any context here, so there's nothing to interpret. We're just evaluating and solving. So we're going to say, okay, evaluate f of 0. So anytime we have evaluate, we know that we're given an input value. Anytime the equation is written in the context of solving, we know we're given the output value. So we'll do all the inputs, all the evaluatings first. F of 0, we're going to go over to our graph. F of x, the x is 0, so that means our output is 2. We're going to go f of 2, we're going to follow up. Our output there is 5. F of negative 3, okay, well at f of negative 3 the output is 0. And f of 10, we go over here. We notice that our function really stops when x is 7. 10 is not in the domain of the function, so we're going to say that this value is undefined. If you can't evaluate a function at a particular value because the function is doesn't have an input there, we say it's undefined. We're going to move on to our solving now. So if we're going to solve when f of x equals 2. We look, this means the y value is 2, and we look, and it looks like, oh, there's a few points. 1, 2, 3, and I'm actually going to highlight those. We've got 1, 2, 3 times when the function has an output value of 2. We're going to estimate this. This is approximate, let's say x is, let's see, it looks like it's like maybe negative 3.9. That's this first one right here. We've got f of 0, that input got us an output of 2, and a little bit past 3, maybe we'll say 3.1. Don't get caught up about stressing out about whether you're approximating correctly. As long as you're in the ballpark, that's fine. I'm going to do the same thing for f of x equals 0. I'm going to look, okay, well, here's when f of x equals 0, and there's 2 clearly marked outputs. That's one when x equals negative 3, and the other when x equals 4. F of x equals negative 5. I'm going to go right here. There's only one time when the output values are negative 5, and that is at, it looks like at 7, so we're going to say at x equals 7. And then f of x equals negative 8 down here, and you'll notice there's no output value that ever reaches negative 8. Now, we're not going to say it's undefined, because an equation can't be undefined. To be technically correct, we're going to say that this equation has no solution. No solution is to an equation that you solve, that undefined is to an expression that you evaluate, if you want to look at that analogy. So we've just reviewed how to evaluate and solve functions and to interpret the meaning if they have one, given an equation, given a graph, and given a table.